I want to take a closer look at this particular set of inverse functions, because doing that is going to help us to understand a little bit more of another way that I can view inverse functions. I want to take a look at what happens if I apply f inverse after I've applied f of x. So I want to look at this function composition. I'm going to take x, I'm going to plug it into f. That's going to do something. I'm going to plug it into f inverse. That's going to undo what we just did. So that should be just x. And in fact, if you compose inverse functions in either order, so if I did f of f inverse of x, that should also undo whatever I was doing, and that should just give me x. Okay? So we're going to be exploring that aspect of function composition a little bit more later on. But notice, if this is my function f, which has me take my input and add 7, and then this is my function f inverse, which has me take my input and subtract 7. Okay. I mentioned that if we plugged in 3 so that we got 10, we could figure out that that was what we had plugged in. Let's just take a look. If I plug in 3 to f, that's going to give out 10. Now right there, that tells me that the point 3, 10 is going to be part of this function. That would be a point on the graph of f. When I do my function composition, I'm taking that 10 and I'm plugging it into f inverse. 10 minus 7, that's going to give me 3. So we got exactly what we thought we should. We started with 3, we did something, we undid it, we're right back at 3. That's how composing a function with its inverse should always work. But notice, what that tells us also is that the point 10, 3 is on the graph of f inverse. The output from f became the input to f inverse, but then the output from f inverse was the original input. So you can see what we've really done is we've just switched the roles of input and output. And that will in fact always be the case. And that's another way that I can think of inverse functions. So if I had f of x was x plus 7, okay, I'm going to go ahead and write that as just y equals x plus 7. And I'm going to label that, that's the original function f. Okay. Now what we just saw was that on f inverse, we switched the roles of x and y. I'm going to do that. I'm going to replace the y here with an x. I'm going to replace the x here with a y. This equation now describes the inverse function. I'm carefully labeling it here because there's nothing about this x that makes it obvious that this is the x from the original function, and this x that says that's the x from the inverse function. This is what tells me that, the fact that I'm clearly labeling it that way. So now this equation describes the inverse function, but it's not in standard form because usually when we have a function, we solve for the output, which is y, not the input x. Well, if I solve for y, I would subtract 7 over. I would get y equals x minus 7. That's exactly the formula that we said was our formula for f inverse. And now I can use inverse function notation so that I can say f inverse of x is x minus 7. And now that makes it clear. That's the y value, but that's the y value on the inverse function. So if I use the name of the function, I don't need this labeling. But in getting there, it's very helpful to just write the function in terms of x's and y's. If I switch the roles of x and y, I now have an equation that describes the inverse function. And then if I solve for that new y value, that gives me a formula for the inverse function. So we can actually write down those steps. To find a formula for f inverse of x given a formula for f of x. I can first of all just write f of x in terms of x and y. So rather than using the function notation, I'll just call the output y. Okay. Then I can interchange the roles of x and y. The result is an equation describing the inverse. But as we just saw, that equation is going to be solved for x. I'd like it to be solved for y. So step 3, I will solve for the new y value. And then generally when you're asked to find a formula for the inverse, you'll be asked to give it using function notation. So rewrite using inverse function notation. That is, switch from y to f inverse of x. Or if your function was named g, it would be g inverse of x, etc., etc. Now, in this case, it was pretty easy to see that that was the function that added 7. And since I knew the inverse function was going to undo that, pretty easy to see that the inverse function was just going to be the function that had me subtract 7. But it's not always that clear to see. Let's suppose I had g of x equals x plus 1 over x minus 2. Now that's a lot more complicated. It's a little bit harder to see what is it that I'm doing and in what order am I doing it in order to just by inspection be able to see what the inverse is. But this technique should still work. So I can say y is equal to x plus 1 over x minus 2. That was my original function. Now I'm going to switch the roles of x and y. So everywhere there's a y written, I'm going to write an x. Everywhere there's an x written, I'm going to write a y. Now here x was written in 2 places, so I've got to write the y in both places. This now describes the inverse function. Now I'm assuming that there is one. If I try to go through this process and I'm not able to uniquely solve for y, that's going to tell me that there isn't an inverse function. But if I'm able to solve for y and get a unique answer, then we'll be okay. So I would want to get the y's out of the denominator. So I would multiply both sides by a y minus 2. Now when I do that, I get y minus 2 times x is equal to y plus 1. The y minus 2's are going to cancel. Now I do have a restriction here that y can't be 2 because I started with a y minus 2 in the denominator and it's not there anymore. So good practice, I'm going to just record that. Now I want to be able to solve for y. Right now this y is linked with that minus 2 inside of those parentheses. I can't separate them as long as they're together in those parentheses. So I'm going to break apart the parentheses by distributing that x. So now I'll have xy minus 2x is equal to y plus 1. Now what I can do is I can move things over. I'm going to move this y over to this side, and I'm going to add the 2x over to the right side. So I'll have xy minus y is equal to 1 plus 2x. Now what I've done there is every term on the left now has a y in it. None of the terms on the right have a y in them. With every term on the left having a y in it, I can now factor out that y. And the beauty of that is when I factor out the y, I'm just writing it once. So here I had to physically write the symbol y 2 times because it occurred twice Now I only have to write it once. I can divide through now by x minus 1, and I'll get that y is equal to 1 plus 2x over x minus 1. Kinda cool, okay? So that's my formula. Now, I do have this restriction here that y isn't 2. Ordinarily, when we describe a function, we would describe any restrictions that we had on the input, which would be our x values here. And here, that's a restriction on our output. I'm going to simply tell you, this actually is never going to equal 2. The restriction sort of takes care of itself. I could actually see this is a rational function. If I were to write it in descending order on top and on bottom, fraction of the lead terms is just 2x over x, which is 2. The graph of this would have a horizontal asymptote at 2. Now I could check to see whether we ever touch that asymptote. It turns out that we don't. So there will be some examples where there are these restrictions. They do always sort of take care of themselves. So I'm not going to require that you write them down, but I would strongly encourage you just in your work to write them down, and then when you get to the end say, oh yeah, and that restriction will take care of itself, or even do the work of confirming that this formula will never spit out a 2. Just because there are times when we're solving equations where recording those restrictions is absolutely essential. This is one of those times where it takes care of itself. I'm not quite done. I found myself a formula. I want to just write it using inverse function notation. So the original function was g, so I would say this is now g inverse of x is 2x plus 1, or 1 plus 2x, the order there doesn't matter, over x minus 1. And that would be my final answer there.